All right, so now we'll look at some specific impacts on the distribution grid. And we've used this figure a number of different times, but let's suppose I'm working for a utility and I want to basically figure out whether a developer can interconnect some distributed generation into the grid. What I need to run is I need to run what's called an impact study or an integration study. And if the unit's kind of small, let's say this is residential, usually most utilities have what they call a fast track procedure where they apply some rules. And if the unit that's being proposed is small, they're just given right away the permission to interconnect. But if it's large, utility needs to do a study on this. And so you just can't have people, hooking PV or other DER into the grid. This all has to be approved by the utility to make sure it's not going to adversely impact circuit operations. So the different sort of things that we'll be talking about is listed here. So we'll kind of talk about, basically what's going on in terms of changes in flows, and we'll look at voltage regulation and flicker protection and things like that. I've got some references at the end which kind of get into this in a little bit more detail. We're not going to have any time to exhaustively cover each item. But if you're doing a study, typically these are the different types of things you need to check against. And so the first is what's going to be the impact and changes in power flow. And as I mentioned before, these circuits are basically set up to operate in unidirection. And so if I've got a circuit and I've got a backbone for the circuit, if I'm going to be interconnecting in, say, like a large DER plant to this particular location, and let's say this is going to be pretty large scale, say this is going to be like 5 megawatts or so. Well, what do I need to look at? Now, if I have a circuit that say like 15 megawatts of load, this is still going to be unidirectional. But if I'm at, say, like some light loading conditions and say like the net load's only like 3 megawatts, then I start getting backfeed into the grid. And so there's a lot of things we need to look at when we start having these reverse power flows. And I mentioned before, a lot of times these wire sizes are set up for what we call tapered load, the load that drops off the further away we get away from the substation. But if I'm suddenly connecting up large amounts of DER, basically, this could cause like overloads on certain wire sizes that weren't just put out there to handle this much kilowatt and kVAR load. And so we have to take a look at capacity constraints. So we need to be worried about that, especially if we get out further away from the substation, like these wire sizes that we have further away are going to be kind of small. And if I try to put 5 megawatts out here, this wire may not have the amperage handling capability to allow that to be interconnected in. Something else that we see as well on these circuits is we also see a change in losses. And so what's going to happen is, if I'm talking about small scale PV, and if I have load out here, actually, if I have small scale PV, let's suppose like residential customers connect up PV, say like 5 kilowatt size units. If this cancels out with the load, this actually has a net beneficial effect. But usually what happens is we're looking at integrating larger scale, like 5 megawatts instead of 5 kilowatts. And so in this case, if I get a significant current flow on the circuit where before I had smaller amounts of current, then what happens is the I²R losses could actually go up pretty significantly. And so again, if we have small amount of DER that matches up with the load, the losses will go down. But if we have large amounts of DER that causes, say, like large current flow in the opposite direction, then the losses would tend to go up. And so this is a couple things you have to kind of look at first is you're concerned about capacity and you're concerned about losses, okay? And you may have to put out larger wire sizes if you're having issues with these. Now, the other thing we run into with putting distributed resources out in the distribution circuit is we have the potential for losing our voltage regulation. Because if I had a regular feeder, the voltage would start high at the substation. As I went further down the feeder, it would drop, 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 drop. And we're worried about that voltage staying above a certain low threshold. Now, if I put DER in the circuit and it's pushing power back in the opposite direction, instead of the voltage continuously dropping, the voltage can drop a little bit, but then when it gets close to the DER, the voltage can actually go up. And so we can run into a situation where we actually have an overvoltage. In fact, a lot of your penetration studies are actually more concerned with overvoltages than they are undervoltages, because the distributed DER could actually push the voltages up too high, especially under light loading conditions. And so this is what you see a lot in these integration, or sometimes that are referred to as hosting capacity studies, is you'll be looking at voltages under light load conditions and see whether the DER is going to push those up too high. This can also be seen on secondary circuits. Now, normally when we analyze distribution, we don't model the transformer and the service drop and look at that voltage. We typically don't do that. But the thing you have to realize is, let's suppose you have 3 or 4 houses put together, and all these houses decide they want to put PV on the roofs. What's going to happen when they're light loading conditions? All these houses pushing power back, say at noontime when the load's light, could actually push the voltage up too high. Now, these PV devices will have inverters on them that'll set the trip out, the voltage gets too high. So really what happens in this case is maybe the household inverters are just trip off. But there's been a few cases where the high voltage could actually cause some damage to loads. And so this would be kind of another sort of a thing that would be looked at in screening analysis, is the utility would make sure it only has so much PV connected up to each residential transformer. A third thing is the interaction with voltage regulating equipment, which I mentioned earlier. So if I have some DER set up on the circuit, what's going to happen is we're going to get a backfeed type of effect. And that may impact the way like a line voltage regulator would work. And so normally these regulators are set up to handle voltage drop. But if you have power flow in the opposite direction, they can get a little bit confused. Something else that would happen in these circuits is what happens if there's variability. So if there's variability, then that causes that regulator to kind of work overtime, right? And that it's continuously trying to adapt to changes in net load in this case. So this is something we have to worry about, would be whether we're still going to be able to regulate voltage the way we would like to if I have excessive backfeed, and what's going to be the additional wear and tear on these regulators, especially this one in the substation. This is an extremely expensive device. If we lose that regulator in the substation, we may not be able to operate the circuit correctly. And so utilities are really concerned about what's going on with the substation tap changer. So regulators are designed, as I mentioned before, to operate in both directions. And the reason we would do this is there is a legitimate reason why power flow would reverse. If we have a, say like a fault upstream, then we may want to isolate it and use a backfeed source in order to provide customers in the opposite direction. And so these are called bidirectional regulator controls. Regulators take a look at the direction of real power flow, and they would actually switch which side they regulate. So instead of regulating V2, they'd actually start regulating V1. Now, what would happen if you had a generator cause a direction in power flow? Well, the tap would start out at a certain position on here, but what happens is that as soon as that regulator detects the reverse power flow, then it thinks it needs to start regulating V1. And what that generator is going to do is going to cause this voltage to go real high. And so what happens is this regulator is going to try to buck the voltage down at V1 as a result of something like that. So here shows this in a little bit more detail, where I could have a certain level of DG out here, and as long as that DG is going to be less than my load, then what happens is the regulators will still work. And so voltage drops down. When the voltage drops down enough, the regulator boosts it up. As we get down to the load center, the voltage drops. And if we had our DG on the opposite side, the voltage would still be high near the DG, but it doesn't really impact the line regulator as long as the net load is greater than the generation. However, as I mentioned in that previous slide, if that regulator detects a backfeed, it'll switch directions because of that. And then what it'll do is the DG causes the voltage to be high. Then what this regulator is going to do is it's going to try to drop it down. And what's going to happen on this side is the voltage is not going to be regulated properly. In cases where we have DG, remember the DG a lot of times is set up to be a current injection. So this DG is not really actively regulating the voltage. It's not actively controlling it. It's just injecting backfeed current that pushes that voltage high, right? But it's not actively manipulating voltage. This is kind of sort of an undesirable side effect. So we always, if the DG is not regulating voltage, we always want the voltage regulators to be doing that, right? But the problem is if it detects this reverse power flow, then it basically assumes that this is a source, a regulated voltage source instead of DG, and then it starts trying to regulate the wrong voltage, and as a result of that, we get some sort of a goofy increasing profile as shown here. So some of these regulators will have what's called like a cogen mode, and it'll actually then turn off the bidirectional capability so this doesn't happen. And some algorithms will take a look at the reactive power flow as well and use the reactive power flow to try to determine what case it should be working on. There's also voltage flicker, and what causes voltage flicker is the intermittent output of some of these sources. So if you have cloud cover, what this does is it can cause the power output to go from 100% of rated down to say like 30% in a matter of so many seconds, right? Maybe like 10 seconds or so. So the issue is that if I've got kind of like a source, and let's say the source has some impedance, and if I have current injected associated with the PV, and if this is varying with time, what happens is this varying current interacts with the Thevenin impedance to give me a varying voltage at this particular point, at the point at which this PV is tied into the system right here. And these could be rather rapid fluctuations, and these rapid fluctuations is sometimes what's referred to as voltage flicker, all right? Sometimes more recently, these have been called instantaneous changes, but this is going to cause a flicker in the voltage. And basically, if I look at the voltage at that point, you're going to see it's going to have a magnitude that's varying with time because of this. Now, this in the past has been associated with issues with lamp flicker, light flicker. So when we had incandescent lighting, what this varying voltage would do is actually cause changes in the lighting output, which actually cause a lot of irritation to like humans and farm animals. And so a long time ago, they developed this, what they call the flicker curve. And basically what they said was that if you're making sure that you're not going to have any issues with flicker causing problems, you needed to make sure that the percent voltage change stayed within a certain threshold. And they talked about this in terms of changes per hour and changes per minute and changes per second. And so if you're talking about changes per hour, maybe you can withstand about a 2.5% change. But if you're talking about changes per minute, then this threshold drops down to maybe like 0.7%. If you're talking about changes per second, it drops down even further. And so this is what's referred to as a flicker curve. And a lot of utilities would still use something kind of similar to this. And so they want to make sure that if you're measuring voltage at a point, that voltage doesn't have too much flicker associated with it. And that's going to be a big issue when you have large scale PV plants that are susceptible to a lot of variations due to, say, like cloud cover. Now, something we can look at to give us an indication about whether this is going to be an issue or not is something called a stiffness factor. And basically what we're looking at is we're looking at how stiff the grid is. So we can characterize this by short circuit current, because the larger the short circuit current, the lower this impedance is and the stiffer the grid is. And so what you would do is you would look at the current injected by the DER source, you would compare it to the short circuit current, the stiffness of the grid. And if this ratio is high, we typically don't see any issues. But if the stiffness ratio starts to drop below, say, like 25, then we get a lot of voltage variability due to variations in DER output. And so this is kind of a rule of thumb here that you could kind of look at, and you may not allow any interconnections where, say, like the stiffness factor gets below like 25. DER also causes a lot of problems with our overcurrent protection that we use on distribution. Basically, we're going to have issues with fuse breaker miscoordination. Reason being, because if I have distributed generation in the field and if a fault would occur, basically what this is going to cause is more current to be dumped into that fault. And so what this means is the fuse, it would have taken a certain amount of time to blow under normal conditions where all the current came from the transmission. Now, if we have additional current that's injected locally, it's going to cause that fuse to blow faster. And so we would lose our ability of having coordination maybe between the breaker and the fuse if we want to do something, say, like fuse savings, or if we wanted to coordinate properly, this could be an issue. Something else we see is what's called sympathetic tripping. And so if I have a fault on one feeder, and if I have a number of distributed resources in another, all these distributed resources are going to feed current into the fault. And what this does is it actually passes through two breakers. And so if I had regular overcurrent on this breaker on the bottom, it might actually cause this breaker to trip when the fault's actually on another feeder. Now, to get around this, nowadays what we use is we do directional overcurrent. And so we can actually measure the phase angle of the current with respect to the voltage, and we can actually detect when the current's flowing in the opposite direction. So that's normally the fix for something like this, but we have to have a more sophisticated relay for that. And then the other thing that distributed generation does in the feeder is it desensitizes our ability to detect faults, say, like from the top of the circuit. So what happens is if I have a fault now, DG is going to pump current into that fault. And if DG is pumping current into this fault, what's going to happen at the top of the feeder is the current that gets supplied by the transmission circuit actually drops down. Okay, so the DG is injecting current now, and that means there's going to be less current injected by the source. And what this means is it makes it harder for this relay to see certain types of faults. So if this fault's way out along the feeder, since that local DG is pumping enough current into that fault, that's a lot less current that gets injected at the top of the circuit. And that could actually drop below the point where it could be seen by the relay, right? And so this can cause some issues as well. All right. So anyway, if this was a protection class, we'd get into this some more, but just wanted to kind of point out some issues you could run into from a protection standpoint. Another issue is whether we get what's called unintentional islanding. And so it's theoretically possible that if I have a circuit and I've got load and I've got distributed generation, that if this breaker opens up, that this section could operate as an island if there's an exact match between load and generation. And so what that's referred to as unintentional islanding. We don't want that to happen because the distributed generation can't handle the voltage on the circuit. This can cause a lot of issues besides operational issues. There's a lot of safety issues associated with this, where we have generators which are feeding what the line workers think are a de-energized circuit. And so this could cause issues with safety. It could damage equipment, cause other issues with voltage. And so if DG loses connection to the grid, and if this is not designed to be operated in microgrid mode, we need that DG to drop off, to trip. And so there's special islanding algorithms that are written into the relay code of the DG in order to trip that DG offline. And another thing we've been seeing more recently are issues with transformer energization Inrush. So if you have like a large PV plant, let's suppose it's like 5 megawatts, well, you have to have 5 MVA of transformer in order to connect up to those inverters. And there's a lot of cases where we're energizing a PV plant from scratch, where all those transformers get switched in a lot of times all at the same time. And there's a huge inrush current. And the reason we have a large inrush current is, let's suppose I'm energizing a transformer. There's a nonlinear relationship between flux density and field intensity. This kind of maps over to, if you're looking at the excitation current, a nonlinear relationship between excitation voltage and excitation current. So because of this, what happens is when we switch, say like a 3-phase transformer in, we don't immediately go into steady state. What happens is a transit where, depending on when we actually close that transformer, some of the phases are going to get a current that are asymmetric. They're not symmetric around the y-axis anymore. And they have a large second harmonic component to it. And it takes a while for this to damp out. And so what happens when we have this inrush current, then this interacts with the system impedance to give us a drop in voltage. And where we run into issues with this, and here's a real case, if I have a substation, and if I have a regular feeder, and let's suppose this feeder has, say, like power quality sensitive load on it, and I've got a photovoltaic plant and an adjacent feeder, it's got a lot of transformer associated with it. Well, if I'm closing the breaker in and all this transformer capacity gets connected to the grid, what happens is there's a large inrush current going through this path. And because this substation and system has impedance associated with it, this large inrush current interacts with the system impedance to give me a large voltage drop at the top of the feeder, which then is seen by the loads within this industrial plant. And so here's a real field recording that kind of shows at the substation, when we close in a large PV installation, this inrush which occurs, and what it's doing is it's causing a dip in the phase associated with the large inrush magnitude. And so these power electronic motor drives, let's say at the industrial plant, see this, and it can cause some confusion. It actually causes these to trip offline. And when you have an industrial process that starts to lose motor drives, it causes a lot of problem with their processes, which wreaks a lot of havoc in terms of expenses. So let me stop here for this part, because we talked a lot of different things. We'll look at some of these phenomena in our project, in part 3 of our project on the Buck Swamp circuit. But just realize that every time like a large DER facility is interconnecting to a distribution grid, there's typically an interconnection study that has to be done by planners. Sometimes these are planners that work for utilities. Sometimes these are consultants that are working for the utility that have to study all these potential sort of impacts and decide under what circumstances this facility can be interconnected into the grid.